Okay, well, I'll get going with the introduction. I'm happy to be here for SGP's Thallium Isotope Proxy Primer. This is a series of um, both live and recorded videos where we try to accessibly introduce a given geochemical system or proxy. And excited today to be talking about thallium. Many of you are familiar with the SGP, but for those who are not, we're an open, community-oriented research consortium that seeks to address questions of environmental evolution across Earth history through statistical analysis of the sedimentary geochemical record. And I would suggest checking out our informational website and our search website down here. Over the years, we've built a database that has more than 133,000 samples with coming up on 5 million analytical results. And this has been built by our collaborative research team with more than 200 people contributing worldwide. We're now jumping into our phase three data acquisition phase and science phase. And in this, we're hoping to get more data from Mesozoic and Cenozoic samples, more Archean samples, and data from carbonates, and data from metal isotope systems. And so that segues well into our proxy primer today with thallium isotopes. And I'm delighted to introduce Dr. Chad Ostrander from the University of Utah, who is a world expert in metal isotope systems. Chad is from Oregon originally, and after high school went into the Marine Corps. I'd like to thank him for his service. After that, he went to undergrad at Arizona State University in Ariel Ambar's lab, and then continued on to his PhD in Ariel Ambar's lab at ASU. Following that, he went to a postdoc at Woods Hole for about 3 years, where he worked with Suni Nielsen and others. And following that, he was hired into his job at University of Utah, where he's an assistant professor. And as I said, a world expert in metal isotope systems, particularly thallium and molybdenum. And so I'm excited to hear today more about the thallium system.
Awesome. I'm going to share my screen now. Is that full screen for you?
Yep.
Cool. Yeah, thank you, Eric, for everything you and your team do with SGP. This is a wonderful resource, and thanks for the invite to talk today, and also for posting these online. This is a really nice opportunity to not only talk to those of you in the room today, but also put something on the internet that'll be around for as long as the internet's alive for people to look at, for better or worse. My name was already introduced in my institution. I'm Chad Ostrander from the University of Utah. And this isn't the first and
Sorry,
only.
Chad, I think we lost the share somehow. I might have messed it up by pinning your screen.
You don't see it?
No, can you try resharing, please?
Yeah, can you see it now?
Yep.
Can you see this slide?
So it's on the presenter view now.
Uh,
Yeah, there.
okay,
Oh,
that's
it
just a
is.
weird looking slide.
Yeah. Okay. Right. So you
Okay,
want to go back to your starting slide?
yeah.
Great. Okay, we're good.
Okay, awesome. Yeah, as Eric said, my name is Chad Ostrander. I'm a metal isotope geochemist from the University of Utah. And this isn't the only thallium isotope presentation that'll live on YouTube. There's also another one that I delivered a few years ago for virtual seminars in Precambrian geology. Some of you, I'm sure, also attend those. That was more tailored to the deep time applications, just a few of them. And this one is going to be more tailored towards modern ground truthing of thallium isotopes, how thallium and its isotopes cycle in the ocean today. And then what does that really tell us about how thallium isotopes can be applied as a paleo-redox proxy? So feel free to go check out that other talk for more information about the deep time applications. Before I get started and before I lose you, I've tried to keep my talk fairly short, just probably north of 40 minutes to keep your attention. But if you learn nothing else from this talk other than these bullets, then that's okay. Thallium isotope and sediments. And because it's tied to manganese oxide burial on the seafloor, it is a really unique tool for indirectly tracking bottom water oxygen. So it's not that thallium isotopes are directly sensitive to oxygen. They're sensitive to manganese oxides, and it's the oxides that are sensitive to oxygen. And because of these unique properties tied to manganese oxide burial, it seems, based on modern data that we have to this point, it's a really good tool for specifically tracking deep marine oxygenation, which some of you might attribute to the ventilation of the ocean. So it seems like a good tool for checking things like that. Right now, it seems to work very well in shales. That is where the techniques and the proxy were developed, but we're also extending it into carbonates, and carbonates are showing some promise. And what we're also learning about thallium isotopes is that they can track really short-term global scale redox change. So even redox change occurring on submillennial, single thousand year timescales. All right, so diving right in. These are the two stable thallium isotopes, thallium-203 and thallium-205. All atoms of thallium have 81 protons in their nucleus. That's what identifies them as thallium. But there's stable nuclear configurations with a different number of neutrons. And so one can have more neutrons in the nucleus, thallium-205. Changes in the relative abundances of the two stable thallium isotopes are typically reported in epsilon notation, epsilon 205 thallium, in units of parts per 10,000 or per myriad. So this looks a little bit different than typical isotope systems, which tend to report data in delta notation in parts per thousand or per mil. But it's essentially the same thing. The isotope ratio differences in theory should be smaller, and so we multiply by a bigger number. But it can be thought of the same way as delta values. Higher values, more positive values, are more enriched in a heavier mass isotope, whereas lower values, more negative values, are enriched in thallium-203. For those of you interested in perhaps dabbling in thallium isotopes, you have a project or a set of samples that you're potentially interested in generating thallium isotope ratio data for, under typical analytical conditions, we aim for about 15 nanograms of thallium. That's the typical run conditions. You can spend more time and do some more boutique measurements and get away with smaller sample masses, but we typically aim for 15 nanograms. And if that's the bar, then ferromanganese nodules and crusts can be extremely enriched in thallium to the tune of 60 ppm and above. And for samples like that, you can get by with even as small as sub-milligram sample masses. Carbonaceous shales, black shales, are what we have applied the proxy to the most. And under typical concentrations for those, you can get by with as little as 20 milligrams. We usually aim for about 80 milligrams to be on the safe side. Carbonates, and this is what kind of complicates these applications. Carbonates are pretty thallium poor, on the order of single to sub to a few tens of ppb. And so when we are doing carbonate applications under these typical conditions, we need at least a gram. We usually aim for about 2 grams of carbonate material. It's quite a bit. If you're really adventurous and you want to do some aquatic systems, thallium is really unabundant in those types of conditions. Seawater, thallium concentration is on the order of about 13 ppb. So to do a good isotope ratio analyses for seawater thallium, you need just over a liter. If you're so brave as to look at lake water, which concentrations are typically on the order of a few ppb, you'll need approaching 10 liters of water, usually what we aim for there. If you go to really anoxic and sulfide-rich water masses, such as found in the Black Sea and the Baltic Sea, the concentrations are even sub-ppb, and you need on the order of tens of liters, which we've done, but it's not fun. And in terms of sample preparation, my training to this point has focused exclusively on solution-based analyses. I'm not a laser guy. So if you are using solutions, lake waters, seawater, then some of these steps are not required. But if you do start with a solid sample mass, we typically, for our applications, don't do bulk digest. You can do a bulk rock digest. Use your own method of choice as long as you can get it into solution. We try to attack specific phases. I'll go into more here in a couple slides, but we try to isolate specific phases. So we'll do some gentle leaching of those phases we want to get thallium out of. Then we will have that sample. It needs to be put into solution, so we'll do some digestion techniques. Use your own. There's more than one way to do this. Use your preferred way of getting things that are solid into liquid form. We have to purify the elements of non-interest, especially those that are isobaric interferences with thallium and will complicate the measurement. And during purification, we also concentrate the thallium. You take a really large sample, for example, in the case of seawater, you can concentrate in a small volume. The thallium is more concentrated. And then we move on to our isotope ratio analyses. So in terms of separation, for the typical shale applications, we try to isolate thallium from pyrite. That is when it's present in sediments, the dominant sedimentary thallium host phase. We do this with a gentle 2 molar nitric acid leach, which it liberates the thallium from pyrite. You can prove that to yourself by looking at thallium concentrations. Here, the subscript A is authigenic thallium. That's the leached component. It tends to trend with things that also track pyrite, like pyritized iron. And this also avoids pesky detritus. We know what the thallium isotope composition of the bulk upper continental crust is. We're not interested in that for most of our applications. It's also harder to digest those minerals. We try to stay away from those. The carbonate applications are still in their infancy, and so we've been playing with a number of different leach techniques. It seems that when the carbonates are manganese lean, or more specifically, manganese oxide lean, it doesn't really matter which leach we use. We tend to we recover thallium isotope compositions in our carbonates that more or less match the seawater that these carbonates are in contact with. When those carbonates have manganese oxides in them, the manganese oxides, as we'll go into detail in the next slides, manganese oxides really fractionate thallium isotopes very strongly. And so when they're in your sample, if you're looking for manganese oxide signal, it's great. But if you're trying to avoid it, then it's a hard place to work. For our carbonate applications, again, we're still working on these. These are fairly new. These methods are published in a paper just last year. We've been doing bulk digestions for a lot of our stuff, and then trying to use trace metal trends to decipher where the thallium's coming from. It's not really known right now where thallium sits in these carbonate samples. Again, these concentrations are really low. It's really hard to tell, and it isn't clear where they should sit. For digestion techniques, it's worth knowing that thallium has a relatively low melting point on the order of about 300 C, and so it's best to avoid high temperature digestion techniques. For those of you who use muffled furnace, for example, to cook off organic matter, that is a problematic technique for thallium if you bake at the typical temperatures, 500 C plus, that those methods usually call for. You can lose your thallium, especially in really organic rich samples. So at various stages in method development and application, we have used high pressure Asher systems to digest thallium. We've also used microwave digestion systems, which work pretty well. We've also just used simple hot plate digestion in Savlex PFA vials, which takes a little bit more time, but can be done. In terms of purification and concentration, it's a pretty simple ion exchange chromatography, column chemistry. It's the same column chemistry repeated twice. At least that's the method that I like to employ. I like to do the same column twice just because the thallium comes out much cleaner. You can get by with a single column, especially in samples that are really thallium rich. Your thallium to matrix ratio is really high. You can get by with a single column. We've shown in some papers that there's no isotope ratio differences between single first double column purification. But some of these applications like carbonates, it would be really hard to clean those samples with just a single column. I like 2 columns just because it tends to be cleaner and that simplifies everything. For isotope ratio quantification, my preferred instrument is the multi-collector inductively coupled plasma mass spectrometer. And this method it's a really simple analytical method. This is a low resolution measurement. If anyone has done stable lead isotopes, it's the same cup configuration. It's basically the lead method in reverse. It's the same cup configuration, but when you're measuring stable lead isotopes, many users like to dope your sample with thallium. We know this machine will fractionate the isotopes, but if we dope the sample with an isotope system that behaves similarly to the one you're measuring, and we can monitor the fractionation on that ratio that we know, we can apply this mass-dependent correction to the lead isotopes. Well, for thallium isotopes, we dope with lead, and so we'll use lead to correct for mass fractionation. But yeah, again, it's a pretty simple measurement. In terms of how good the measurements can be, what our typical long-term reproducibility is under typical run conditions, we achieve a long-term reproducibility of about 0.3 per myriad, which is really good. That is much smaller than the 30 per myriad variability we observe in nature. If you do get into some of those more boutique measurements where you're having to use less thallium, maybe you have a smaller voltage, a smaller ion current coming to the detector, then you will have to expand that 2SD. It does go up in a predictable pattern. All right, so any paleo-redox proxy, in my mind, must be able to do two things very well. The first thing that a proxy must be able to do or must have is a unique redox sensitivity. If a redox tool doesn't have a unique redox sensitivity, it can't tell us specific things about redox, and some tools fail in this regard. The other thing that a paleo-redox proxy must possess is a reliable archive for tracking this sensitivity. And for thallium isotopes, it actually satisfies these two criteria fairly well. Eric had mentioned early in my introduction that I've worked with molybdenum isotopes in addition to thallium, in addition to many other isotope systems, but molybdenum isotopes, for example, don't do a particularly good job of either of these things. And that's why I've kind of shifted to using thallium isotopes quite a bit. Thallium isotopes are uniquely sensitive to manganese oxide minerals. In this figure on the left, you have thallium isotope compositions on the x-axis and thallium concentrations on the y-axis. That's a log scale. Those are big changes. And nothing is more enriched in thallium and more enriched in thallium 205 than ferromanganese nodules and crusts that form on the deep oligotrophic seafloor. This is a really strong fractionation mechanism. In just a little bit more detail, thallium isotope fractionation effects that exceed 10 per myriad, so exceed a per mil. 30 per myriad equates 3 per mil fractionation in the system. That is a lot of fractionation for such a heavy element. Mass fractionations scale typically with the relative mass differences of the isotopes being fractionated. Hydrogen fractionates a lot because the mass difference between hydrogen 1 and 2 is double. Thallium 203 and thallium 205, the mass difference is really small. You shouldn't expect a lot of fractionation, all things being equal, but nuclear volume field shift effects associated with the large size of the thallium nucleus can drive fractionation effects that are much larger, in this case on the scale of tens per myriad. In order to do this, it helps to try to have thallium redox reactions take place. And so if you can oxidize thallium plus to thallium 3 plus, you can kick in this nuclear volume field shift effect that can drive these large fractionations. And this just so happens to happen on this with some manganese oxide minerals. Specifically, hexagonal bernesite is a mineral that has vacancy sites large enough where thallium can get in and be oxidized to thallium 3 plus, and this mineral drives a huge 20 to 30 per myriad isotope fractionation effect. So again, it's not that thallium isotopes directly are sensitive to oxygen. Thallium isotopes are sensitive to manganese oxides, and it's the manganese oxides that are sensitive to oxygen. And manganese oxides, you've seen all of you in some form in your career, these redox ladders, and it's really hard to have manganese oxides be stable without a stronger oxidant around. In most natural environments today, that stronger oxidant is oxygen and nitrate and nitrite. At the same time, it's really hard to have considerable nitrate and nitrite without a stronger oxidant to keep that abundant. So oxygen is that that strongest oxidant that helps stabilize everything below. And so without oxygen, you have no nitrate. Manganese oxides are then the thermodynamically most favorable oxidant, and they tend to deplete rather rapidly. And so in the absence of oxygen, manganese oxides tend to dissolve, and the manganese gets spit back into solution, or if there's enough manganese around and the chemistry is right, then you can start to form manganese carbonates. But at any rate, this is reduced manganese, and so you really need the oxides to stabilize the oxygen to stabilize the manganese. So again, just to drive that point home, as is the case with all proxies, they don't usually directly track oxygen. It's another process in the middle. In this case, it's manganese oxide formation. Nearly all of the thallium isotope variability found in modern marine sediments is attributable to manganese oxides. Again, this is a really unique effect. We're really lucky that thallium isotopes are subjected to this surprisingly large fractionation effect during interactions with manganese oxides. And really, no other process can drive the same magnitudes of fractionation. You can get some scatter from other isotope fractionation processes, but those fractionation processes are about an order of magnitude smaller in magnitude. And so you can look at sediments, for example, from modern upwelling zones, and the thallium isotope composition of that sediment on the y-axis here is dictated, it has a predictable relationship with manganese contents. So manganese contents on the x-axis are a pseudo proxy for the stability of manganese oxides in those sediments. Sediments that have more stable manganese oxides fall to the right on this diagram, and they're shifted positive because those manganese oxides are fractionating thallium isotopes. When those manganese go away, uh, those manganese oxides, then there's no fractionation, and the sediments actually measure seawater. So seawater is -6 per myriad. These lowest values that are manganese lean, they essentially capture seawater. And so just to drive this point home, there's some things that I'm going to talk about in this presentation that I didn't want to labor in detail here for this specific presentation, but I do have a large number of supplementary slides that during the non-recorded portion of this talk, I'm happy to go into more detail about any of these things. And this is the first such slide where I do have supplementary slides that get these points across in more detail uh, and can help you appreciate the things that I'm about to say with these slides. But strong fractionations require not just manganese oxide formation, but long-term burial of manganese oxides in the sediments. We've been studying manganese and thallium cycling in different redox stratified settings today, where manganese oxides can form and are stable in oxygenated surface waters. But as you go deeper in these water bodies, the waters are anoxic, the manganese oxides sink, they dissolve, and the thallium is also spit back into the water column. There's no net fractionation in the sediments from these settings. So we've seen this in the Baltic Sea. We've seen this on a euxinic pond on Cape Cod. We've seen this in a ferruginous lake in Minnesota. We can see small isotope fractionation effects from the manganese oxides between the waters and the particles as these oxides form. But as these oxides sink and start to make their way to the lake bed, they do not carry that thallium isotope fractionation to sediments. So again, if you form manganese oxides in surface waters, if you work in the Archean, this is really important for ideas like manganese oxidizing phototrophs or photooxidation processes for manganese oxidation. Those processes seem inadequate to explain thallium isotope fractionations. We've also been studying sediments in the Baltic Sea. The Baltic Sea is a really unique environment where twice per decade on average, although with less frequency recently, the Baltic is subjected to these major Baltic inflow events. The Baltic Sea is a euxinic anoxic environment, but for a few months out of the year, twice a decade, these well-oxygenated waters come in from the North Sea, and you get these really impressive manganese oxide burial events in these otherwise anoxic sediments. The sediments become oxygenated for a few months. And when this happens, it leaves no measurable impact on the isotope composition of the sediments for thallium. So these short-term manganese oxides that are surviving for just a few months do not lead to isotope fractionations that get retained in the sediments. The thallium gets spit back into the water column. And so even short-term seasonal manganese oxide formation cannot drive fractionation effects. The biggest effects that we see for thallium isotopes are on the deep oligotrophic seafloor, where manganese oxides are stable for millions of years in the case of ferromanganese crusts and nodules. So this leads to a pretty neat relationship, I think, for thallium isotopes. Here on the y-axis, you have the isotope ratio difference, or rather the epsilon notation difference between the sediment and the seawater. And so values of 0 are, these sediments have the same isotope composition as seawater. As the values get more positive, the sediments are more strongly fractionated because of manganese oxides. You seem to get larger thallium isotope fractionations with depth. The photic zone, sediments formed in the photic zone, the data density is pretty poor. But you don't see large manganese oxide fractionation effects. You go a little bit deeper to the mesopelagic zone, and you start to see a little bit of manganese oxide imprints on the sediments, but it's not until you get to the really, really deep seafloor, over a kilometer depth, that we start to see these really large manganese oxide-driven fractionation effects. And this could suggest that thallium isotopes are, again, sensitive to not just manganese oxide formation, but long-term burial, and especially long-term burial on the deep seafloor. That's the strongest lever. All right, so the sensitivities of thallium isotopes to manganese oxides also become apparent when you start to think about seawater thallium mass balance. All of the thallium that enters the ocean today has, on average, and in mass, roughly the same isotopic composition of about -2 per myriad. That's the same value as the bulk upper continental crust and bulk silicate earth. Thallium isotopes do not strongly fractionate during weathering processes, during processes that deliver thallium to the ocean. The most important thallium delivery mechanism to the ocean today is subaerial volcanism. It accounts for almost 50% of thallium delivery to the ocean today. The second most important thallium input is rivers. It accounts for just over 25%. After that, high temperature hydrothermal fluids, so on-axis hydrothermal systems, do constitute a net source of thallium to the ocean. It's on the order of about 20%. The mineral aerosols are another quantifiable thallium source to the ocean today. Again, you can see little variations from site to site. For example, one river or one volcano will have a slightly different thallium isotope composition as another one. But if you average those sources in a global fashion, they all have an average isotope composition that's about the same at about -2. There has been some cases made that oxide dissolution in reducing sediments, for example, in upwelling zones where manganese oxides can be formed in sediments, but then dissolve seasonally, for example, during OMZ expansion, the manganese oxides dissolve. This can lead to the net release of isotopically heavy thallium, but it's not quite clear whether this is a quantifiably important source. If it is, it could result in a slightly high isotope composition delivery. Seawater, by contrast, has a much lower thallium isotope composition of -6 per myriad. So this, just from a simple standpoint, requires an output mechanism from the ocean that has a strong preference for heavier mass thallium isotopes to drive seawater isotopically light, to get rid of the foreshadowing its manganese oxides. The residence time of thallium in seawater is about 18,500 years. That's longer than the global ocean mixing time of about 1,500 years, which means that thallium is globally distributed, both in concentration and has a conservative profile. Its isotopic composition does not change from basin to basin or with depth. And the thallium concentration of seawater is about 65 picomolar, or 13 ppb. So in terms of outputs, again, this really low seawater value requires an output with a strong preference for heavier mass isotopes. That output is oxic sediments, primarily on the deep sea floor, can drive huge fractionations. This average value is 18 per myriad, larger than seawater. This is a huge fractionation effect because of those nuclear volume field shift effects. The most important thallium output from the ocean today is low temperature seafloor alteration. So off-axis hydrothermal systems that are circulating cold seawater do have a preference for the lighter mass thallium isotope. On average, this fractionation, however, in a global net sense is pretty small. It's about a -1 per myriad fractionation effect. Reducing sediments in OMZs, you saw that figure a few slides ago, are quite variable, and it depends on the manganese contents of those sediments. Some of those sediments capture seawater, so they're -6. Some are slightly positive because they're manganese oxide contributions. Euxinic sediments do not fractionate thallium isotopes as well. The thallium isotope composition of these sediments is the same as the overlying water column. Anoxic reducing euxinic sediments account for a quantifiably important amount of thallium removal on the order of about 6% or so. Carbonate sediments do not fractionate thallium isotopes either. This is just based on data from the modern Bahama Bank. So more data collection is required, but it seems that there's no fractionation there as well. The concentrations in these sediments are so low that it's probably not a quantifiably important output from the ocean, however. So in terms of what can drive an isotope paleoredox proxy, one of the ways I've been liking to frame it is in terms of isotopic leverage. So here we have the different thallium isotope compositions in sediments from different basins today and different sites in the ocean. And here is that capital epsilon value. This is the difference from seawater. The red values near zero do not fractionate thallium isotopes relative to seawater, and the values that are really positive are driven heavy by manganese oxides. The oxic pelagic seafloor has really, really high thallium isotope compositions because of manganese oxides. The x-axis rather here, this is the thallium accumulation rate in these sediments. And so some sediments, like sediments forming in euxinic basins and in modern upwelling zones, they actually bury thallium quite fast. The thallium removal efficiency is really fast. There's really no large isotope fractionation. You can see that with the little movement on the y-axis. The manganese oxides remove thallium extremely slowly. So there's a lot of isotopic leverage with this output. The oxic sediments on the deep sea floor can drive substantial thallium isotope fractionation effects, but the removal rate of thallium is so slow that they must cover a large area of the seafloor in order to be quantifiably important. To really sway seawater isotope mass balance like they do today, they need to cover a large area of the seafloor, which they do today because the seafloor is mostly oxygenated. This sink would be much more impactful to have much more isotopic leverage if it buried thallium much more quickly. For example, if oxic sediments were a really efficient thallium removal mechanism, they could drive really large seawater differences, even if they covered small areas of the seafloor. Perhaps that was the time. There was a time in the past when that did happen, but in the geologically recent past, it's probably unlikely. For those of you who are interested, after the recorded portion of this talk, I do have supplementary slides with the same figure for molybdenum isotopes and uranium isotopes, if you want to see how those isotope systems plot in this space. So in terms of, again, paleoredox proxies must be able to do two things very well. One is have unique redox sensitivity. Seafloor manganese oxide burial is what thallium isotopes seem to be uniquely sensitive to based on data from all the modern sites to this point. They seem especially sensitive to slow manganese oxide burial on the deepest seafloor. I've tried to make that point. And so in terms of what's the redox sensitive signal that we need to track, the second important piece of this paleoproxy fundamentals is that you need to have a good archive for tracking this sensitivity. That the seawater thallium isotope value is that redox sensitive signal. The seawater value is dictated by the globally widespread distribution of manganese oxides. That's the signal that we want to track. That's the same case for molybdenum and uranium isotopes. For those tools, the general premise is the same. You want to reconstruct a seawater isotope composition and make some mass balance arguments tied to redox. So now we'll talk a little bit about the archive for tracking this sensitivity. What archives capture the seawater thallium isotope composition and allow us to reconstruct these values in the past? So we've been focusing most of our efforts to this point in reducing sediments, so shales formed under reducing conditions. We can find out that independently with things like iron speciation or trace metal distributions, among other things. If our shales or carbonates were formed under reducing conditions, based on what we see in modern equivalents, they should capture the seawater value. Euxenic sediments capture the thallium isotope composition of the overlying water column in places like the Black Sea, the Baltic Sea, Kyriako Basin, the Santa Barbara Basin. If upwelling zones have really manganese-poor sediments, so very little manganese oxide contributions, they can also capture the seawater thallium isotope composition. And again, carbonates can also do that. I'll return to this when I talk about the weaknesses of thallium isotopes. Thallium isotope compositions in individual euxenic basins, you do capture the seawater value of that individual basin, but individual basins can have different isotope compositions. And so basin restriction is an important weakness for thallium isotopes. So in order for this to happen, in order for an archive to capture the seawater isotope composition, one of two things needs to be happening. Either the dominant sediment thallium host phase, in the case of reducing sediments, pyrite, does not drive a quantifiable isotope fractionation for thallium isotopes, that's a possibility, or thallium removal in these systems approaches quantitative. And so if all of the thallium delivered to a water body is removed to sediments, there's no opportunity for isotope fractionation. And so perhaps near quantitative transfer of thallium from the water column to sediments leads to the direct capture of those values. It's really hard to tell which one of these processes is happening for thallium isotopes. I tend to lean towards the idea, based on the data I've seen and generated, that pyrite tends to not drive really large fractionations. But again, this is something we're still trying to figure out. The carbonates is really hard to figure out because the contents are so low. So here, in terms of seawater archival, these are different environments shown in box and whisker form. Here's the sediments from the Great Bahama Bank. Here are sediments from euxenic basins, continental margins, and the oxic pelagic seafloor. These are the cap epsilon values. Again, this is the difference relative to seawater. Things that plot on the red line do not fractionate thallium isotopes. Things that are positive are offset by manganese oxides. Oxic pelagic seafloor, very different from seawater. We know that because of the manganese oxides. Continental margins can skew in that same direction because of manganese oxide burial. Euxenic basins, this is normalized to their individual water columns, do not fractionate thallium isotopes, it seems. The carbonates do not as well. For those interested in seeing these plots for molybdenum and uranium isotopes, I also have those at the end of my slide deck. So the basic premise of the thallium isotope paleoredox proxy has now been conveyed. We should be able to use some ancient marine sedimentary rocks formed under the right conditions for capturing seawater values to track changes in those past seawater values and tell us things about manganese oxide burial changes at a global scale. You can make a couple of simple predictions that if Earth's oceans at any given time underwent extensive ocean deoxygenation events, you would expect to see a positive shift in the seawater thallium isotope composition, which is, again, that's what we're hoping to track. And that would signify that heavier mass isotopes are not being preferentially delivered to manganese oxides that can accumulate in seawater. And so we've seen this in the first application of thallium isotopes to shales across oceanic and excavant 2 in 2017 at two different sites. As you go across the boundary that signifies OAE2 based on carbon isotopes, the thallium isotopes shift in a positive manner at two geographically distinct sites. And so this was neat to find, and it showed us early on that indeed this really simple prediction was satisfied during oceanic and excavant 2. Shortly thereafter, another set of scientists, Teddy Tem, Jeremy Owens, and others showed that this also happens during Tawarshan anoxic oceanic and excavant, the TOAE, Tawarshan oceanic and excavant. As you enter this event, based on carbon isotopes, you see a positive thallium isotope shift. What was neat about these studies was that the thallium isotope shift predated the carbon isotope shift, and so we tried to make some claims on ocean deoxygenation predating the organic carbon barrel that signifies these events. See those papers for more interest, for more details. Another simple prediction that you can make for thallium isotopes is that during global scale ocean oxygenation events, you should see the opposite. You should see a shift to really low values. For example, values approaching modern seawater if oceans became as well oxygenated as today. And this signifies the burial of manganese oxides over large areas of the seafloor, again, somewhere else on the ocean. So the shales we target capture the seawater values. They're not burying manganese oxides. We're tracking manganese oxide burial changes at other locations. And so one data set that I thought showed this quite nicely is just an updated compilation of thallium isotope data through time. The yellow data points signify time binned averages, and all the values are crustal, around -2, which is again the same as global ocean inputs, and only start to get really low until like the early to mid Phanerozoic. And so many geochemical hawks are swirling right now on the Paleozoic, as perhaps that time in Earth's past when ocean ventilation became a long-lived feature of the Earth. And thallium isotopes through time seem to track that as well. You don't really see really low, consistently low thallium isotope compositions till about the rise of land plants, which is neat. Although there are some exceptions to the rule, we do see some negative blips at different time frames, and we've written about that in some papers. I have a lot of these applications I do have summarized in my summary slides as well, or my supplementary slides. For those of you interested in looking at individual timeframes in the past, I have a lot of those figures, and we can talk about thallium isotope cycling in the Ediacaran during the rise of animals, across the Great Oxidation Event, or even during the rise of land plants. But here it's nice to see that this proxy, if it does really track ocean ventilation, it changes when ocean ventilation seems more likely. All right, one other really unique thing we're finding out about thallium isotopes is it responds to global ocean redox change really rapidly. Yi Wang at Tulane University has been showing this very nicely. Is that if you look at the geologically recent past, you can generate in sedimentary rocks formed under the ideal conditions for capturing seawater values really coherent thallium isotope trends in the geologically recent past. The scale is flipped here. Note that higher up means more negative, but you see over single to a few thousand-year timescales, coherent shifts in what seems to be the seawater thallium isotope composition. These shifts are even more quick than the residence time, the response time of thallium, which is interesting and could have to do with thallium's linkage to the manganese cycle. Residence time of thallium in the ocean is 18,500 years, and so it should respond on those types of timescales. It's responding much faster. The manganese cycle, which it works through, has a much shorter ocean residence time of 17 years. So perhaps really non-steady state short-term shifts in manganese cycling in the global ocean can get thallium to respond much more quickly to redox change. So it opens up this tool for tracking really short-term change. Molybdenum isotopes can't do this. Uranium isotopes can't do this. Those residence times for those elements in seawater are on the order of many hundreds of thousands of years. Another thing that our research group has been trying to do is for some time now, we've been looking at shales or carbonates that capture the seawater value, and they tell us that manganese oxide burial is changing somewhere else in the ocean, hopefully globally. But another way you can use the tool is let's look for that actual complementary evidence. Can we find the complementary evidence for the manganese oxides? That might manifest in the form of positive correlations between thallium isotopes and manganese contents. Sediments with higher manganese contents are more likely to have had some manganese oxide contribution. And if there was manganese oxides in the original sediments, then you would expect them to have isotopically heavy values. And in an unnamed unit, for specific reasons, I show that we do show this, and it's pretty neat that you can actually find evidence of the oxides in those original sediments. Again, not everything is perfect with the isotope system. No isotope system is, no paleoredox proxy is. There are some clear weaknesses to the thallium isotope paleoredox proxy. Some really obvious ones are restricted basins are an Achilles heel for the system. Different restricted basins today, again, you can still transfer the seawater value to those sediments in those basins, so long as those basins weren't bearing manganese oxides. But the individual basins have their own isotope compositions. This is because the seawater thallium content is quite low, again, 65 picomolar. So these restricted basins aren't very well buffered with large amounts of thallium from seawater. And in these settings, thallium inputs to the basin are not coming primarily from seawater, they're coming from rivers, or in some cases, like the Baltic Sea, anthropogenic inputs. And so because it's not very well buffered with a high concentration in the seawater, like molybdenum, individual basins can have their own isotope compositions. What is kind of useful here, though, is that it should have a predictable value. If thallium into these basins is coming primarily from rivers, then it should have a value of -2. And so you do have a prediction you can test with that hypothesis. For the carbonate applications, again, we're just starting these applications, and it's not as smooth as the shales. The low thallium contents do add predictable complications. You need larger sample masses, which complicates the chemistry. It can make the analyses slightly harder as well sometimes. And because these contents of thallium are so low in these rocks, they're much less likely to be rock buffered. So when you think about diagenesis, the relative concentration of your element of interest in diagenetic fluids versus the solid, in this case, the thallium content of the salt is really low. And so any small addition or subtraction of thallium from that system from diagenetic fluids can affect the system. To try to work through these early applications in another way, what our group has been doing is we've been pairing shales and carbonates together. Shales, we have a better idea of what they should give us. Do carbonates show the same thing? Do they show different things? So that's kind of how we're moving to that space. In the short residence time of thallium, it's a double-edged sword. So the short residence time allows us to capture really rapid timeframes of global redox change, but at the same time, it's more likely that the seawater thallium residence time at some times in their past could have been shorter than the ocean residence time, and that would lead to a heterogeneous distribution of thallium in the ocean. It would really dampen the use of this tool as a global scale redox proxy, be more of a local scale indicator. Molybdenum and uranium isotopes, the molybdenum and uranium systems have much longer residence times. It's much harder to push those residence times lower than the ocean mixing time. So again, there are benefits, but also weaknesses to that short residence time. And we need to appreciate that when we apply thallium isotopes. But just to kind of reiterate the strengths here, I hope that I've conveyed to you that thallium isotopes are a really unique tool, and they do have a really unique sensitivity. Thallium isotopes are uniquely sensitive to seafloor manganese oxide burial, not mere manganese oxide formation. Because of this, they seem like a really good tool for tracking indirectly bottom water oxygenation. They are especially sensitive today, based on what we've gathered from modern settings, to not just bottom water oxygenation anywhere, but perhaps bottom water oxygenation in the deepest depths of the ocean, the sediments that cover the vast majority of the ocean floor, deep ocean sediments. They work best in shales, but they also work in carbonates, and we're working through that. And they can, in some circumstances, track really short-term submillennial redox change. So this is my final slide. I'd just like to iterate that after the recorded portion of this talk, I have a bevy of different supplementary slides that we can talk about if anybody's interested. I have these isotopic leverage figures for molybdenum and uranium, see how they kind of work in that space. The same archival figures for molybdenum and uranium, how effectively are those seawater values transferred to sediments. I have some expansions on the manganese oxide burial specificity. Specificity. I also have a supplementary slide talking about the mineral-specific isotope fractionation effects. It turns out that which manganese oxide you form is important for thallium. There's also various deep time applications, and I've included a ternary diagram that shows you how you can shift seawater thallium isotope values by changing the different outputs. But with that, I'd like to, if you're interested in thallium isotopes, reach out. Here is a QR code to our website where you can see some of our papers and what we do and who we are. But with that, I'd like to take any questions that you have for those of you that have them. Thank you for listening.
Great. Thanks so much, Chad. That was really awesome. Um, I am going to turn off the recording now and we can get on to the questioning period.